In the previous video, we were talking about solar energy, and I noted that one of the major drawbacks for solar is that unless you have a way to store the energy that you're creating, you can't use solar to generate electricity 24 hours a day, because as soon as the sun is gone, well, that's it for solar. And the problems of storing the energy come with their own issues, infrastructure issues and environmental issues as well. And there's ways to solve that, but that was the previous video. However, as the sun is moving around the Earth, it is differentially heating different areas of land and water, creating rising and expanding air currents and cooling and falling air currents, high pressure systems and low pressure systems. And even when the sun has left one location, the way the air currents move as a result of the sun continue to change and adapt long after it's gone. So the wind, which gets its energy effectively from the sun and the Earth's rotation, is kind of a form of energy that is available 24 hours a day, originating from solar, that doesn't have that same drawback. So let's talk about wind energy a little bit. One big pro of wind energy, in addition to being able to be used 24/7, is that it has the potential to produce 40 times the current global use of electricity. That is, if we were able to put wind farms, all over the place, get all of the wind available here, which obviously is, a lofty goal, but it is possible to get enough electricity from just wind to meet all of our energy demands. This quote is from your book, The Statistic. With subsidies and government support and smart grids, we'll talk about smart grids a little bit later on, Atlantic and Gulf Coast wind farms could generate more electricity than all of the United States' coal-fired power plants currently do. And even without full cost pricing taken into consideration, wind power is the least costly way to produce electricity. So, wind is cheap. Wind can meet more than our current energy needs. Wind is able to be installed all over the place. It doesn't have the same limitations as, say, a solar farm does. Wind is renewable. Wind mills do not create any greenhouse gases. This seems like a pretty good option, so let's take a look at it a little bit more closely. You will not be shocked about this. Wind power relies on turbines. If during the first video where I was talking about electrical induction you were only half paying attention, maybe it's a good time to go back and check it out, where you have a coil of wire in a magnetic field. Anything that can spin that coil will generate an electric current. And what's going to spin that coil here is the wind. We're going to get the power from the windmill blades. So the windmill blades are attached to this chassis, which is called a nacelle. And inside the nacelle is the gearbox and the generator, which is our turbine, essentially. The gearbox has a large wheel on it, which is directly attached to the windmill blades. And it's got a lot of teeth on that big gear. And then it's attached to a smaller wheel with also a lot of teeth on it. And the fact that you have this big wheel attached to the smaller wheel means that for every partial turn of the windmill blades, you get a full turn of the smaller wheel, right? Every time this big wheel takes one big turn, you're going to get several spins of that smaller wheel. As a result, as the windmill blades are spinning, the generator is going to be turning many, many, many times faster. You're going to get a lot of electric current even though the windmill blades are only moving so fast. And that, pretty simply, is how windmills work. Probably the easiest one that we've had. So, wind turbines can be located on land or at sea and can produce electricity at very low cost. Wind farms provide about 8% of U.S. generating capacity, which is more than any other renewable source, and they are also the fastest growing renewable. Solar's fast, but wind is fastest. Now, like a lot of the statistics in my slides, this one is a couple of years old, not that old, just a couple. Of the 200 gigawatts of electrical generating capacity that the United States has added since 2007, 1/3 of that capacity came from wind farms. So when I say it's a fast-growing energy sector, it is really fast. Like, this is one of the largest growing energy sectors that we have. And just like with nuclear and solar, where I was talking about new technologies that could improve it in the future, there's some new ideas that could make wind turbines even more efficient. So this gentleman right here is a marine biologist by the name of Frank Fish. That's right, he's a marine biologist, but it is called Fish. And he teaches at Westchester University, actually. He was my zoology professor. And he developed a kind of windmill blade that has these tubercles on it. He based it on a whale's flipper. He had studied the hydrodynamics of how whales swim through the water, and he realized that these tubercles reduce drag as the whale is moving through the water. And he thought, hey, wouldn't that be a cool thing to adapt onto a windmill blade? So he tried it, and it made the windmills way more efficient. So you get similar energy outputs with these windmill blades at 10 miles an hour as a conventional windmill blade would get at 17 miles an hour. So not only is it a cheap form of energy and a fast-growing form of energy and able to deliver a lot of power for us, but the technology is still developing. It could get even better from here. This is a field called biomimetics, where we take ideas from nature and we apply them to technology in order to improve it. And if you ever get into design and engineering, you might be shocked how much biomimetics comes into play. Now, every energy type has pros and cons, so what are the cons of wind power? Well, wind farms do require a large area, and it kind of needs to be cleared out in order to install all these windmills there. So that leads to habitat destruction, modification, and fragmentation. However, with windmills, after they're established, you can use the space underneath them for farmland or just let it kind of regrow as habitat, as a large field. With solar, you can't use the land underneath the solar panels for farmland because the solar panels are competing for sunlight, but with wind, you can. Right? So you can utilize that space for different reasons. Sometimes flocks of birds fly through windmill farms, and several 100,000 birds are killed annually in the US every year, somewhere between 140,000 to 328,000. That statistic was from an academic review article published in 2013. The link to the source is there in the slides. If you are interested, you want to check that out. Now, for context, oil fields, because you always have to compare these forms of energy to each other, kill 500,000 to 1 million birds annually. So windmills are not even the biggest killer of birds in the energy production industry. Devil's advocate, that's somewhere around 3 or 4 times the number of birds. Oil produces somewhere around 4 times the amount of energy, so per kilowatt hour, they're maybe about equal. However, 365 to 988 million birds die a year from window collisions, just running directly into windows in buildings. So a similar number to those killed in oil fields, much, much higher than the number potentially killed by windmills. And additionally, house cats that are allowed outside kill billions of birds annually, mostly songbirds. So while this is a concern, in context, this is not, one of the main issues affecting bird populations. However, wind turbines are the leading cause of mortality in bats, and this is according to another academic review paper, this one published in 2016. Bats are substantially less likely to run into a building or be eaten by birds, but a windmill blade, which is constantly moving, if they're using echolocation to determine if there's an object in front of them, there might not be an object in front of them initially, and then by the time they get there, the windmill blade is in front of them and hits them. So that is an ecological concern of windmills. And finally, I don't think anyone needs to be told this, but in the off chance you do, as long as we're on the topic, no, the noise created by windmills cannot give you cancer. That is not a thing. If you don't know what I'm talking about, don't worry about it. We're just going to move on to hydrogen fuel cells from there. So, solar, as we've noted, has an energy storage problem. Wind also, to a lesser degree, has an energy storage problem because the wind's not always blowing, so it would also be handy to have a way to kind of bank excess electricity for later when the wind's a little bit lower. You could charge up an old-fashioned battery, but that requires acids and sometimes toxic metals and mining materials out of the ground. So hydrogen fuel cells are a different kind of energy storage solution to a more traditional kind of battery. So in order to understand how they work, we need to talk about just a little bit of chemistry. It's going to be the easiest chemistry ever, I assure you. So hydrogen fuel cells, as the name implies, involves hydrogen, which is a chemical element. So these are atoms of hydrogen right here, and you can already see that they are the simplest atoms that we've seen. You guys saw helium in the first video, you saw some uranium, krypton, and barium in the nuclear energy bit here. They were much more complicated atoms though. Hydrogen is just one proton, one positively charged particle in the center, and one electron, one negatively charged particle around the outside. It is the simplest and most abundant element in the universe. Most matter in the universe is hydrogen. Okay, so we're never going to run out of this stuff. This is a resource that is amply abundant. And one reservoir of hydrogen that we have amply available to us is water, which covers 75% of the Earth's surface. So if we create a lot of electricity using some of these intermittent fuel sources, solar and wind. Intermittent means that sometimes you have them, sometimes you don't. So solar and wind are intermittent fuel sources. And obviously you could use any other kind of electricity as well, but I'm just going to use renewables in this example. You could do what's called electrolysis. And electrolysis means that you're running an electric current through water molecules. And a water molecule is a single oxygen atom attached to two hydrogen atoms. That's why it's H2O for water. Two hydrogens, one oxygen. So if we get two water molecules, we run electricity through it. What it does is it splits all of those atoms apart from each other, and they will reform in different combinations. So you'll end up getting hydrogen gas. So now we have elemental hydrogen here, and we have oxygen gas. Okay, so these are the byproducts of electrolysis right here, just hydrogen gas and oxygen gas. No carbon dioxide, no methane, nothing like that. We started with water, we end with hydrogen and oxygen. But we're going to keep those. We're going to store them in two containers here. You can see these two cylinders that are undergoing electrolysis right here, and we're getting separated hydrogen and oxygen gas in them. This can potentially be very clean, releasing no greenhouse gas emissions. Now, if you were to mix the hydrogen and the oxygen together, you could ignite that and get a combustion reaction. You would get an explosion, a little explosion, and you could design an engine that runs on just that, right? That splits water molecules into hydrogen and oxygen, then recombines them together, has something like a spark plug to ignite them, and then you have a combustion engine that basically runs on water. These cars have been designed. A fuel cell doesn't quite work like that, though. There's a little bit more complexity to a fuel cell. So here's a diagram of a fuel cell. On the left-hand side in this yellow area here, you see you have a fuel chamber that is filled with the hydrogen gas. So we run some electricity and we produce lots and lots of hydrogen gas, and that fills up this chamber here. Now remember, hydrogen atoms are just protons and electrons, one proton and one electron. So periodically, the hydrogen atoms are going to bump into this negative electrode. And another thing that you should know about hydrogen is it does not have a very strong grip on its electrons. So those electrons might start moving through those wires, leaving only the positive proton behind. And that's what an H+ is. A hydrogen ion is just a proton floating around. Those can move through this proton exchange membrane, this blue area in the center, and they make their way over to the right-hand side chamber, where the the electrons revisit them, right? Because now there's all this positive charge over here on the right-hand side chamber. And the positive charge on the right now is creating the pulling force to get all these electrons on the left-hand side to move through the wires. So you get this continuous motion of the electrons from the left over to the right, but they have to go through the wires, while the protons take the shortcut to go left to right through this membrane in the middle. This is a specially made material that only allows positively charged things through it. All of these things will combine back together, the electrons, the protons, and then oxygen from the air, and they will combine together in order to form water, the waste product. So the fuel cell just generates water as its waste product at the end. But in the process of doing this, of slowly allowing the hydrogen gas to be stripped into its component parts and then eventually combine with water, you get an electric current because you force the electrons to move through these wires. Incidentally, if you did the combustion reaction, you just put oxygen and hydrogen gas together and then lit a match or something like that, the byproduct would also be water. You would get water as the end result. So this is the same reaction. You're getting pretty much the same amount of energy out. You're just getting it in a much slower, more careful, precise, controlled kind of way. So I'll go through the motions one more time. Number 1. In the negative electrode, hydrogen is stripped of its electrons, leaving hydrogen ions, protons, H+. The electrons move from the negative electrode to the positive electrode, creating electric current, creating electricity. So the electrons move through the wires. Meanwhile, the protons traverse the membrane. In the positive electrode, water is formed when oxygen combines with the protons and the electrons that flow from the negative electrode. Okay. So that's, like I said, it's pretty much the easiest chemistry you can imagine. If you understand that each hydrogen atom is one proton, one electron, and you understand that the protons can move through the membrane, the electrons can move through the wires, then you pretty much understand how this fuel cell works. The other thing to know is that when these two combine with oxygen, then you're going to get water coming out, H2O. I have this animation here of a fuel cell. It's okay. It shows hydrogen and oxygen going into their respective chambers. The hydrogen is stripped of its electrons. The electrons move through the wires. Then you see the hydrogen and the oxygen come together to form water. The only thing I don't like about it is that the electrons kind of lag behind, and the hydrogen and the oxygen cannot bind together to form water without those electrons coming along as well. So the electrons should be moving just a little bit faster so they can jump onto this water molecule at the same time. Otherwise, this is a pretty good idea of how it works.